Hello, student. Welcome back to this chapter of fiber optics. So in this session, I am going to discuss what is the distortion or dispersion. So in an optical fiber communication system, the information is coded in the form of discrete pulses of light, which are transmitted through the fiber. These pulses of light are characterized by width, amplitude, and interval. So these parameters change. Actually, they are increasing when the pulses propagate through the fiber. This is known as distortion or pulse mode dispersion. Because of this reason, the pulses may overlap at the output end and may not be resolved. This is expressed in terms of nanosecond per kilometer. So there are two types of dispersions. One is the intermodal dispersion and another one is the intramodal dispersion. So intermodal dispersion is the dispersion which is taking place in one mode, whereas intramodal dispersion takes place when there are one mode of propagation of light inside the optical fiber. This intramodal dispersion is further divided into two types. One is the material dispersion, another one is the waveguide dispersion. So first we will see what is this intermodal dispersion in step index multimode fiber. So this is a step index multimode fiber. It is a multimode fiber. You can see this is the fiber, and when you look at this diagram, it is very clear that the diameter of the fiber is more. So that indicates that the fiber is a multimode fiber, and this N1 is the refractive index of this core, and N2 is the refractive index of the cladding as usual. So this red path indicates the propagation of the light signal or light ray inside the optical fiber. So this I is the angle of incidence at this point E, and this dotted line indicates the axis of the optical fiber. So this ray, when it enters the optical fiber, makes an angle theta with respect to the axis of this optical fiber. And this ABC represents a pulse of light or signal inside the optical fiber. So consider the propagation of a pulse through a multimode fiber. The fiber associated with the single pulse, it gets distributed. Sorry, the power associated with the single pulse gets distributed into the various modes or paths guided by the fiber. The pulses of lower order modes travel a greater distance than the higher order modes. As a result, light pulses broaden as they travel down the fiber, causing signal distortion. Hence, the output pulses do not resemble the input pulses. So because of this broadening effect which is taking place, the output signal is more broader as compared to the input signal, and hence they do not resemble with each other. So this type of distortion is known as intermodal dispersion or simply modal dispersion. So here I am going to derive an expression for the time delay due to intermodal dispersion. So consider the path of a particular mode which propagates, making an angle theta with the axis of the fiber. So this I have already shown in the diagram. The time taken by a refracted ray to traverse the distance ABC of the fiber would be tau dash. Tau dash is equal to AB plus BC divided by V. So this ABC is a pulse. So actually we are counting the time taken by the light to move through a distance equal to the pulse width. So ABC is a pulse here. So AB plus BC is the actual path traversed by the light divided by velocity gives the time. And this I am writing as AB plus BC divided by CN1. So by making use of this fundamental relation between the velocity of light in a medium, velocity of light in vacuum, and refractive index, this relation already we have it. So by making use of this relation, I write I will replace this V with the C by N1, and here you rewrite it, so it becomes N1 by C into the bracket. This N1 by C1 we have written here, and this one AB is written as AD by cos theta by diagram. So this AB is there. Its projection on the optic fiber is AD, so it is AD cos theta. So this AB is its projection on the optical fiber axis is AD by cos theta, plus BC is also the path of the ray traversed by the light. So this BC, again, this is also the second half of the path traversed by the light in one pulse, and its projection on the axis is CD by cos theta. By diagram, it is very clear. And here we'll write this N1 by C as it is, and cos theta is common here, so it becomes LCM. It is AD plus C divided by cos theta, and this is equal to N1 by C into AD plus CD. From diagram, it is AC, so it is AC by cos theta. So in this equation, as I explained, this V is equal to C by N1 is the speed of light in the core of refractive index N1, and C being the velocity of light in the vacuum. Thus, the time taken by the light to traverse a length L is equal to tau is equal to N1 into L divided by C cos theta. So this tau dash is equal to N1 by C into AC by cos theta is the time taken by the light to traverse a distance equal to one pulse, but this is the time taken by the light to travel some length L inside the optic fiber. So for the axial ray, theta is equal to 0, then this cos theta, cos 0 becomes 1, and we are getting a minimum time. So that is tau minimum is equal to N1 L upon C. For the axial rays. Axial rays means the rays which are moving along the axis of the fiber. For the rays that travel the longest path, that means the paraxial rays or the rays which are moving near to the cladding. So they take more time as compared to the rays which are moving along the axis of the cable. So in such case, when theta is equal to theta c, the critical angle, the time taken by the rays to travel this much of length will be a maximum. So that we are representing as a tau maximum is equal to N1 into L divided by C cos theta C. So we got two times. One is for the rays which are moving along the axis of the cable, and this is for the rays which are moving near to the cladding surface. Since the critical angle theta c is equal to cos inverse of N2 by N1, this already we have got the result in earlier session. So the equation 3 will write as here cos theta is there, this one cos theta c is there, so that we can write as N2 by N1, and so this becomes this N1 goes up, so it becomes N1 square L upon N2 C, and a total time delay between the arrival of the axial ray and the slowest ray is given by delta tau, and this is equal to tau maximum minus tau minimum. So we have to subtract this time with the maximum time. So we are getting this as N1 into L divided by C into the bracket N1 by N2 minus 1. So this is the expression for time delay, and this in terms of the refractive, and this is in terms of the refractive index of core and cladding, because N1 is the refractive index of core and N2 is the refractive index of cladding. So in terms of fractional refractive index change delta, this equation can be written. So delta is equal to N1 minus N2 upon N1. We know this relation from earlier sessions, and this equation can be written in this way. And in equation 5, this N1 by N2 minus 1 is there, that is replaced with delta divided by 1 minus delta. So the equation 5 becomes delta tau is equal to N1 into L divided by C into the bracket delta divided by 1 minus delta. So this is the expression for the time delay in terms of the fractional refractive index change, which is delta here. So in terms of numerical aperture, so the equation 5 we'll write in this way. It was N1 by N2 minus 1. So that you write as N1 minus N2 by N2. And this is equal to N1 into L by C. And this is written as it is here. And here we are multiplying and dividing by N1 plus N2 and N1 plus N2 here. So this N1 plus N2 is multiplied and divided here. And this N1 minus N2 into N1 plus N2 gives N1 square minus N2 square. And here this is N2 into N1 plus N2. So it is N2 into N1 plus N2. And we will approximate that N1 plus N2 is equal to 2N1. The reason is that the refractive index of core and cladding are nearly equal to each other. So that is why we can approximate N1 plus N2 is nearly equal to 2N1. And so the above equation becomes on delta tau is equal to N1 into L divided by C. And here n1 square minus n2 square divided by this 2 n1 plus n2 is written as a 2 n1 and into n2 is there, and this n1 get cancelled. So we are left with L divided by 2 n2 into C into Na square. So actually we are left with here it is n1 square minus n2 square, that is nothing but a numerical aperture. So we got the numerical aperture in the equation. And what is this now? This expression what I obtained just now is the expression for time delay in case of step mode multi-index fiber, multimode fiber. And what is this expression for graded index fiber? So in a graded index fiber, light rays travel at different speeds in different parts of the fiber because the refractive index varies throughout the fiber. So near the outer edge, the refractive index is lower. Thus, rays near the outer edge travel faster than the rays in the center of the core because the velocity of these rays depends upon the refractive index. Because of this, all the rays arrive at the end of the fiber at approximately the same time. In effect, light rays in these fibers are continuously refocused along the axis as they travel down the fiber. This leads to a small pulse dispersion, and the pulse dispersion in this case, that is in terms of graded index fiber, is given by delta tau is equal to n2 into L upon 2C into del square. So this is about dispersion in graded index fiber. And in the next session, I am going to explain what about the dispersion by material itself. We'll see in the next session. Thank you for listening.